Okay, so hi everyone. So today we're happy to have Daniel Tubbenhauer from the University of Zurich to talk about categories of tilting modules or mind your poles.
Yeah, thank you very much for the invitation and the kind introduction. It's always a pleasure to come to the States without even leaving my home. That's how it works nowadays, I guess. Okay, so I hope you can hear me and I hope you can see my screen. Otherwise, complain to Arik. Um, so I want to going to talk about something I got obsessed with quite a few years ago, and I was pretty sure for a long time that the question you will see on the next slide is pretty much impossible to solve. And then it turns out that actually you can say something reasonable, and it's actually pretty nice. And that's what I'm going to explain. I hope that everything will be very general at one point, maybe one point in my lifetime, who knows. But for today, I will basically stick to some kind of SL2 case, trying to explain it in such a way that you hope at the end you understand that up to some highly non-trivial computations you need to do, the whole philosophy should kind of generalize to kind of all types you can assume, you can imagine. So I want to ask a very simple question. The question is very simple. The answer in general, well, as I said, I was just thinking this is just hopeless, right? It's just an hopeless problem. So the answer, the question I want to ask is, okay, I have a nice category. In my case, it's tilting modules of some kind of reductive group. I will explain everything. Don't worry if you've never heard about tilting modules or whatever. And I will just ask the question, can I describe it as a category? Right? So you look up the literature, and what you very often see is, or what people usually do is they describe the objects of the categories, the modules. I'm not really interested in the modules. I'm wanting to ask a categorical question. I want to ask the question whether I can understand the morphisms in this category and their relations. A very naive question. So formally speaking, as you can see in the middle of my slide here, what I'm looking for is basically some kind of nice algebra such that projective modules over that algebra describe my starting category. Okay. In some very nice way, something like sending indecomposables on one side to indecomposables on the other side. So kind of all the combinatorial properties of my category tilt should be captured on the right-hand side, which is much easier to handle. Okay. So very simple question, right? So the question itself should be easy to understand. You have a category. It's not really abelian, but you have some additive category and you're looking for some nice algebra such that a plot or a projective module of that algebra is equivalent to your starting category. I will try to sell you a certain philosophy, you will see that. And the first example you should keep in mind is if my field here would be of characteristic 0, and everything is algebraically closed, blah, blah, blah. So you can think about complex numbers if you want. Then tilt G would be just G mod. And it would be a semi-simple category as well known by work of several people that will show up in my talk. And this question is pretty easy to answer. Namely, I could just, in this case, for my ZP, I could just put infinitely many copies of my ground field, namely one for each simple module in my category. Right? Simple modules, you have Schur's lemma, home spaces are trivial, so you just have some very easy curve, just a lot of vertices and no edges at all. And it turns out that if you make this a little bit more complicated, it actually gets quite nice. So the answer is in this case, I expect it to be extremely nice. I expect it to be extremely hard to prove. Okay. So for today, just SL2. Okay. So that's my question. That's the question I want to answer today. I have a nice category, which I will describe. And I want to find a hands-on way to present it. I want to understand its morphisms. Right? The morphisms between modules and their relations. Okay, question. So before I'm going into details, and if you want to fall asleep during my talk, just stay awake for this one more slide, because it's really a nice theorem I want to sell here. And it's super old. I mean, it's called Lucas theorem or quantum Lucas theorem. And the quantum Lucas theorem goes back to the 60s. And the Lucas theorem itself, you can see it on the slide, it's ridiculously old. And it's pretty easy. And it tells you something about how to compute binomial coefficients. So it's a pretty easy setup. Just take, well, let's do quantum. I will forget quantum in a second, but let's do quantum. And I call it the quantum characteristic of my field is just the first vanishing of the quantum number. If you just don't like quantum, then it's just a characteristic of my field. And what I would do is I want to compute the binomial of A and B. And what I do is I express it periodically. And I only care about the zeroth digits. That's the A0 and the B0. And I kind of ignore the rest. And then the binomial itself over A and B simplifies as this product of those two binomials, right? You take out the zeroth digit and you have a remaining factor depending on the remaining digits. All right. So what I kind of want to sell you today is, I'm zooming in the last bullet point case in a second, so characteristic P, and I want to tell you a certain philosophy which is hidden behind the whole story of those tilting modules over reductive groups. So kind of the generic case, so characteristic 0, complex numbers, everything is fine. It's kind of the easiest case you can imagine. It's kind of generation 0, right? So everything is just generation 0. It's just, everything is just newborn and no descendants at all. Everything is semi-simple, right? Think of my quiver. It's just a bunch of vertices with no relations at all between them. The next hardest case would be the quantum group. I'm not going to talk about the quantum group, but the quantum group, as you will just directly see on in a second, which follows from this Lucas theorem, will be kind of a generation 1 version. So if you ever wonder what is the relationship between semi-simple and the quantum group and the root of unity, well, it's a little bit more complicated. And then there is this mixed characteristic case, which I just throw in because some people like mixed characteristic, basically can ignore it. And then at the very end of the spectrum, there's characteristic P. And as you will see, characteristic P, it gets completely fractal. It's really beautiful. There's some fractal geometry hidden. And it's just infinitely more complicated than the quantum group. So that's kind of the philosophy, right? Semi-simple, generically, everything is semi-simple. It's characteristic 0, it's generation 0. Quantum group is a little bit more complicated, just generation 1. And generation infinity is infinitely more complicated. This is characteristic P case. So just for the experts, there is a good reason why we understand characteristic 0. And we pretty much understand the quantum group case. So for instance, there's a pretty explicit formula for the quantum for the characters of those modules, the simple modules of the tilting. But characteristic P is just so much more complicated in a very beautiful way, as you will see. And kind of, I want to sell that all this follows from this one theorem here. So let's analyze the theorem a little bit more. So let's say my field is really just of characteristic P, and I don't have quantum at all, right? Q is 1. Then actually what the theorem tells you, just look at it, the quantum is the usual binomial times the quantum binomial, okay? But if the quantum binomial is the usual binomial, well, you can apply the theorem recursively again on this M over N. And this just tells you the following, that's Lucas theorem. The binomial of A over B in characteristic P is just the product of the binomials of the digits in periodic expansion, right? So whenever I write those expressions, I really mean just the digits of the periodic expansion. Okay, so this is really a nice difference that you can see immediately here from the theorem between characteristic P and let's say root of unity, because in root of unity, well, you would just be stuck after the first step. There's a usual binomial. It's just some number in, let's say, in the complex field. It's just what it is. But in characteristic P, you can keep on going and make everything just keep on going recursively until you've done the whole periodic extension. So let me give you a very explicit example. Don't look too much at the numbers, just to give you a flavor. So if I take 11 cubed, that happens to be that funny number, 1331, and I take B to be 11 cubed minus 1, just to make my life easy, then you would apply the theorem. Let's look at it again. You want to compute A over B. So the first thing you want to know is what is the quantum characteristic? And the quantum characteristic in my first example, if ground field is C and Q is 1, well, it should be 0, right? So the binomial is just a binomial. In particular, it doesn't vanish, right? Binomials do not vanish over the complex numbers, for sure not. Second case, if you take K equals C, but now you plot in this 11th root of unity, my Q, then the quantum characteristic is actually 11. So what you're supposed to do in this case is you express A and B 11 radically and ignore everything in front, just use the zeroth digit, and the binomial simplifies as follows. You just get some scalar in C, and you get a quantum binomial. And in this case, you have 0 over 10. 0 over 10 is definitely 0, so this guy vanishes of order 1. There's also this mixed case. In case you're interested, you can look it up. So my slides will be online anyway, or you can rewatch the video. So I'm going to basically ignore the mixed case. The mixed case is kind of a mixture between the quantum case and the characteristic P case. So let's focus on characteristic P, the last example. So I take now, instead of 11th root of unity, I just zoom into I just use my field of characteristic 11. The quantum characteristic is the same, right? It's still 11. 11 is 0 in characteristic 11. But now you do a different game. You express A and B periodically. I've done this for you. So A is just 11 cubed, so it should be 1, 0, 0, 0, 0. And B is 11 cubed minus 1, so it should be 0, 10, 10, 10. So now it tells you that the quantum binomial, or the usual binomial in this case, is just a product over the digits. So you have 1 over 0, which is 1, 0 over 10, which is 0, 0 over 10, which is 0, and 0 over 10, which is again 0. So this actually now vanishes on order 3. Right? And I kind of want to sell you the point, and you will see this in action, that everything kind of that matters is this vanishing of certain binomials like that. If you think about it carefully, and if you zoom back to this theorem, then over the quantum group, there's just no way that this binomial vanishes of any order higher order than 0. It might not vanish, but if it vanishes, then it vanishes of order 0. In characteristic P, it can vanish of any order. In characteristic 0, it never vanishes. That's kind of what I mean by generation. Right? It gets kind of more and more complicated. Okay, I hope this is clear. Let me go back to the theorem. Pretty easy. You can express binomials in terms of products along the digits of a p-adic extension. That's basically what it says. It's a very nice theorem. It's very useful in practice. So basically what I'm going to do is I just do characteristic P because it's so nice. And I want to keep you in mind if you want to see it on kind of a map. So characteristic 0 is your starting point. It's easy, generation 0. Quantum group is a little bit more complicated. And at the very, very infinity, just away from everything is characteristic P. And if you understand characteristic P, you should be very happy. I'm always very happy if I understand the characteristic. Okay, so let me now, so please keep that in mind. That's kind of the philosophy I want to sell. So everything should be infinitely complicated, and everything should kind of depend on a certain p-adic extension of something. And everything, p-adic numbers are basically built, you will see a picture in a second, to give some fractal patterns. So everything should be in the end fractal in nature. But let me start with a very classical story, and kind of to also set up the general picture. So this goes back a long, long time ago, right? You can see it is already 100 years, let's say it's 100 years ago when Hermann Weyl actually started to study reductive groups. And as everyone, you would start with SL2 and you would write down what is nowadays known as a Weyl model. These are just the symmetric powers of the vector representation. So in particular, if you write them down, just the basis vectors, I will write down the action in a second, then it looks like this part of Pascal's triangle, right? You have, well, the trivial module has just one vector, and this is a vector representation, the second one, and so on. This is the second symmetric power, and so on and so on. Note here one little thing. So I always have some, just for the experts, I always have some row shift here. So the highest weight of 1 minus 1 is 0. So this is the 0-dimensional, the 1-dimensional one. But I'm not caring about the number 0. I'm caring about the number 0 shifted by 1. So I'm always interested in this number, the v here, the v here in my expression upstairs. Okay. Just keep that in mind. So I always have this funny notation where I have a -1 somewhere. It's just because there is a row shift. Anyway, don't worry about it too much. So how does the action work? Right? So it's just symmetric powers. The action works as follows. You send a matrix from SL2 to the matrix whose columns are expansions of the binomials, of those binomial coefficients. In action, so really live, if you would have, for instance, delta 6, 7 minus 1, then, well, that would be the extension of this matrix. Okay, a lot of terms, but the point is everything is kind of like here in the first row, for instance, this is just a plus c to the 6 expanded, right? And of course, the coefficients that turn up here are binomials. Right? I told you about binomials before. Right. So that's pretty easy. And what Hermann Weyl actually already did, I'm not sure how much he cared about the characteristic P case, but basically what he already did is the following. In characteristic 0, you can observe that this funny matrix upstairs here has actually no common eigensystem. So it depends on A, B, C, D, and there's no common eigensystem. So actually, this basically proves that this guy is simple. There's no fixed subspace. In characteristic 2, something funny happens. In characteristic 2, right, this 20 here, 20a cubed, c cubed, that certainly dies, and a lot of other entries also die. And you can already see the common eigensystem. There's a common eigenvector here. So certainly this guy has a submodule, namely the one spanned by this eigenvector. And indeed, it's not simple. We just found an eigenvector, but basically by just looking how binomials vanish. Okay, so this is kind of the setup, right? I have those Weyl modules, and in characteristic 0, they are simple, all of them. In characteristic P, in this example, characteristic 2, something funny happens with those entries, right? They kind of become smaller. They kind of submodules pop out of nowhere, in some sense. And that's this funny. Well, you can generalize this. I mean, this is certainly pretty old. I know it from Janssen's thesis from the 70s, where he basically proves that this Weyl module is simple if and only if the corresponding binomial doesn't vanish, and this is if and only if the if and only if case if in p-adic expansion you have just one non-zero digit. And just think about characteristic 0 again. 0-adic expansion, you just have one digit at all, right? There is never ever any more digits. So in characteristic P, those guys are basically never simple. I will always have those funny boxes turning up to tell you something about the general story. In general, you would have a Weyl module and a dual Weyl module. They're usually sometimes also called standard or co-standard modules, and they're parameterized by dominant weights and so on. They behave nice, as you would think they are. And the point in general would be that they're really the simple modules in characteristic 0. So they have the classical characters. They're defined integrally, and they have the classical characters given by Weyl's character formula. All of our beloved formulas. Let me click on this link here for a second. So let me just go back. So the simples given as symmetric powers, as the Weyl modules, sorry, not the simples. The Weyl modules are symmetric powers, and by just checking what kind of binomials vanish, you could cook up this theorem yourself. Okay. And you wouldn't be surprised that, so here's another example in characteristic 5. Everything in purple, so up to here, this is a fourth symmetric power. The fourth symmetric power in characteristic 5 is still simple. The binomials you see are not big enough to be divisible by 5 in some sense. And afterwards, it kind of falls apart. So delta 5 has a submodule given by those two extremal vectors. And here's the delta 6 has a submodule. Sorry, the submodule, yeah, that's correct. This is the quotient. So, the wrong way around. The quotient is this one, and the submodule is this one in the middle. And similarly for the others. And actually, these guys arrange themselves in a very funny Pascal triangle, which you should expect if you know if you believe my philosophy of vanishing binomials, according to a characteristic 5, where, well, let's say here would be a while module along this line, and this is one where the while module itself is a simple module, and otherwise you can read off, well, in a fractal way, the simple factors, like I sketched here in my small example. Right, so for the while modules and the simple modules, you already get this this funny fractal behavior just by looking at the vanishing of the binomials. All right, and before you ask, it's of course an open question in general how to write down the simple characters for the reductive group. But in SL2, I basically told you how it works. I will make it extremely explicit for the tilting modules, which has basically the same answer, not quite, there's a little shift, and I don't want to worry about this case too much. It's basically the same story as you will see in, well, let's say 5 minutes. Okay, get back to the setup, while modules, standard modules, whatever you want to call them, and they're nice, they're defined integrally, they have the usual characters, but they tend to fall apart in characteristic P. Okay, the opposite, okay, so while modules sitting in the middle and a little bit smaller are the simple modules, right? By this philosophy, the simple modules are always smaller than the while modules. You also have the opposite, you have bigger modules, and these are the tilting modules. So if you like, right, this is my goal. If you like finite dimensional algebras, for instance, then the tilting module, you should think about the tilting modules as the correct analog of projective indecomposables or projective modules for the reductive group. The projective group in characteristic P does not have any finite dimensional projective modules, so people needed to come up with some analog of that, and the right analog are tilting modules. So what are tilting modules? So tilting modules form a very nice additive category like projective indecomposables would, and well, I just like to define them today as being the direct summons of tensor products of my vector representation. Remember, delta 1 is just my vector representation. So indecomposable tilting modules for today, by definition, are the direct summons of the tensor product as a vector representation, which should remind you a little bit like how you would define projective, well, maybe not how we would define, but how we could characterize projective indecomposables in the case of finite dimensional algebras. It would be the indecomposable summons of, well, direct sums of the algebra itself. It's kind of the analog here. And in this formulation, I think it's kind of a natural question to study those. If you see the abstract definition, a little bit mysterious why you should study those. Like the abstract definition is exactly my first bullet point. They have infiltration by those delta modules and the nabla modules. Let me just comment on the nabla modules for a second. In general, there's a kind of a contra-gradient dual, but in this case, it's pretty easy. It's just transposing the matrix. So you have two of them. They're kind of dual. They both have the same characters. They both have, they are both defined integrally. And yeah, well, the standard definition that you find in all textbooks and papers of tilting modules would be that you have a delta and a nabla filtration. But as I said, it's in this case, and in almost all cases you would cook up, it's equivalent to being a direct summon of a tensor product of a faithful module. In this case, a vector representation. It's not quite true in general, but it's true enough. And they share exactly the same properties. Let's think about projective indecomposables of finite dimensional algebras. Right? They have the same, you have the same number of them as simple modules. In my case, simple modules are parameterized by dominant weights. So for SL2, just by the natural numbers, indecomposable tilting modules are parameterized by integral rates. That's great. They are highest rate modules, so the corresponding simple will appear as the hat of the module with multiplicity 1. And they have this nice reciprocity, which is basically saying that there's a nice base change matrix. I will come back to this in a second. And the main crucial property of them is that you can, okay, I'm interested in understanding the home spaces. The first step to understand home spaces is certainly to understand the dimension of the home spaces. And for tilting modules, it's actually pretty nice. You don't have to go all the way down to the simples to understand the the home spaces, but the dimension of home spaces is just given by combinatorial datum, namely by counting the multiplicities of the Weil or standard Weil factors. And I really call this Schur's lemma for tilting modules. Remember that these should be analogs of projective indecomposables. There's no way that anything like Schur's lemma should hold for them. But this is pretty close to Schur's lemma. So let me click on this. Let me click on this. Let me click on this button for a second. And what I just said is basically equivalent to in rep G, so representations of my reductive group. If I take the Grothendieck group, I have three nice bases actually. Namely the Grothendieck classes of the simple modules. Okay, that's trivial, not quite trivial, but easy. The Grothendieck classes of the standard modules, co-standard modules, the Weil modules. Why? Because each Weil, I haven't said it, but each Weil module has a simple hat, which is a corresponding simple module. So you have a unit triangular base change matrix between them. And the same is true for the tilting modules. Each tilting module has a simple hat, which is the corresponding simple module. So there's again a unit triangular base change matrix between the three bases. And again, just on the Grothendieck group, by the way, you can't see the difference between delta and nabla because they have the same character. So yeah. Now comes the point. You know the characters of the deltas. They have the classical characters. So all you want to know is basically this number if you are interested in the characters of the tilting module, so the multiplicities. Because this will tell you the base change matrix, and if you know the base change matrix, you could write down, you could invert it and write down the characters for the tilting modules, and by the funny property called reciprocity, you can then write down the characters, the simple characters. So that's what people usually want to do if it's kind of the first question you would ask. It's not quite my question, but it's the first question you would ask. Can you write down the simple characters? Writing down the tilting characters is a more complicated problem in some sense. So what I want to do is I want to consider the following trick. Right? So I showed you how these Weil modules fall apart into simple modules. They get smaller and smaller and smaller. And I want to do the following trick. I want to take a tilting module, and I just want to define kind of a generic version of it, which I call T bar. Okay, so on the Grothendieck group, I can just certainly do that by just mimicking this direct sum here. This is a sum here, and I just want to define a module that I call T bar. Then the end of T bar is just given by counting those multiplicities, exactly in the same way as you would count the multiplicities if this would be a semi-simple case, right? If this would be semi-simple, it's exactly how you would calculate the dim of the end of the tilting module. And in particular, kind of dim of the dimension of spaces of the tilting module kind of don't depend on the characteristic. They're the same as in characteristic 0 in this case. Okay, so what do I want to do? You will see this in action in a second. I actually want to think of, okay, now I have my delta modules. My delta modules, my Weil modules, by definition, in characteristic 0, they will be the indecomposable sums of any kind of tensor product I take, okay? Because it's semi-simple and they are the simples, so they will just appear. In characteristic P, that's not quite true. Why? Well, you will see it. Certain idempotents are just not idempotents. They are just, so you get some, so everything is defined over the integers, and you get a lot of pseudo-idempotents. They spit out some eigenvalue, and this eigenvalue tends to be divisible by P. If it's not divisible by P, what do? You take the eigenvalue, you take the pseudo-idempotent divided by the eigenvalue, and you get an idempotent, and the idempotent splits some module from your tensor product. And this is just not happening in characteristic P, as I said, because its eigenvalue will in general be divisible by P. It's kind of the opposite what I did for the simple modules. For the simple modules, I found an eigenvector in characteristic P. Now I take a certain operator and has an eigenvalue, which is now divisible by P, and so it just gets nilpotent. Okay, again, I will do everything explicit in a second. So the philosophy now should be okay, delta modules, standard modules, they are defined integrally. So no matter what my characteristic is, there's certainly somewhere in those tensor products. And now just take those idempotents and characteristic 0, take them together. None of them is well defined. Everyone might have some poles, which kind of some eigenvalues divisible by p. Just sum them together and you get a well-defined idempotent which splits off exactly this copy. So in characteristic 0, what I just said is the idempotent splitting of T overline in characteristic 0 is just not primitive. You can decompose it first. It turns out in characteristic P it will be primitive. And this is just your indecomposable summand, which by definition has all the others sitting inside, but they don't split off. Okay? Because you don't have an each individual term is not an idempotent, but rather nilpotent element with an eigenvalue divisible by 0. Anyway, we still have this kind of Schur's lemma philosophy in those tilting categories. So let me explain you now the decategorified story if you want. So what can you say about objects if you know this philosophy? And I haven't said it, but of course the eigenvalues of my operators, so the idempotent splitting of the deltas in characteristic 0, they're given by binomials, right? Shouldn't be too surprising, I hope, at this point. And there's a very explicit way to do this then in general. So how many Weil factors, or how to compute those Weil factors of those tilting modules. So here's an example in characteristic 11. You have some very huge number here in characteristic 11, whatever it is. It doesn't matter, you just express it periodically. Here you go, so 140771. And the only thing you care about is how this actually vanishes for everything lower. And you can check that it actually vanishes in order 4. Right? So this is not 0. And this is just one example. It's a maximal vanishing, appears for this, well, whatever, for this number. And you realize, oh, this is divisible by p to the third. Right? This is exactly what I said. So it vanishes of order 4. So it has, and it turns out that this means that there's 2 to the 4th Weil factors, which you can write down completely explicitly. Similar, same example. This funny number in characteristic B, what do? You express it periodically. And how to find the Weil factors? You take all the digits, you don't care for the leading digit, but everything else, and you invert the signs. And for each sign inversion, you get a new number, which you just sum up like this below. But don't worry that they are minus signs, just sum them up naively. P to the 0, minus p to the 0, minus 7p, minus 7p squared, and so on. And well, you get this number in this case, and you know that this one appears. And these are all the Weil factors, right? Let me just say it again, because it's, so you just express your number periodically, right? That's what you should have learned. Because of this Lucas theorem, you just look at the digits. You don't care for the 0 digits. You don't care for the leading digit. The leading digit is kind of unimportant. And all the other digits you can invert or you can't invert. Right? So you have 2 to the number of non-zero digits possibilities, and each one of them corresponds to a Weil factor, and each Weil factor arises in that way. In short, I've just given you a relatively explicit formula for the tilting characters, because now I know all the Weil factors. Now I know my base change matrix between the tilting modules, the tilting modules and the standard modules. So I can just do the base change and express the tilting characters in terms of Weil's character formula, right? Remember, the characters of the Weil factors are well known. They're given by Weil's character. Okay, right. So I just using the Lucas theorem, I just solved it's similar for the symbols. I just solved the question about the tilting characters and the simple characters for SL2. And this just gets, let's say, a little bit more complicated. For other groups, it just gets much, much more complicated, of course. But basically, the philosophy is always the same. You have some funny vanishing of binomials, which kind of then depend on your root system and so on. And to get the combinatoric straight is so horribly complicated that nobody has really ever done it. So already for SL3, this problem is still pretty open to write down the tilting characters. But for SL2, you get a very nice answer, which kind of gives you a hint how it should look like for SL3. And all the conjectures, let me just say this, for other ranks, for other type of groups, let's say SL3, they all have kind of, as I said, like kind of a fractal binomial pattern along the different roots of your root system. Here you just have one root, so you just need to worry about one binomial. Okay, so what have I explained up to this point is what tilting modules are today and what on earth, well, how to solve the problem on the decategorified level. I haven't told you anything about morphisms yet. And that's exactly the point, right? Up to this point, okay, this was known to Janssen in the 70s. Janssen never had a definition of tilting modules in the 70s, but up to that, this was known to Janssen in the 70s. And certainly to other people as well, and maybe even much earlier. So you know all this, you know Schur's lemma for tilting modules, you know the dimension of the home spaces, you know explicit character formulas and everything. And still you can't write down those, you can't solve the categorical question. You can't write down those morphisms between the tilting modules. You just know that there is some, and it has some properties, and that's basically it. And it's very surprising. So maybe the problem I wanted to start with is pretty hopeless. And it was pretty hopeless. So 15 years ago, I would have said this is pretty hopeless. And now comes the main trick, which is kind of in the general philosophy of some newer parts of representation theory. You should formulate the problem in terms of some combinatorial problem, in terms of easier problem. So let me sketch how that works, and then let me show you the result. Before I sketch how this works, I won't click on all those links. As I said, the slides will be online anyway, so if you want to click on those links. This is basically my strategy, and I really would do the strategy in any type, right? There is one problem for any type. At the moment, the strategy has one sin, namely, in order to work out the strategy, I want to know what T bar is. And in order to know what T bar is, I need to know the tilting characters, which is just not possible for the quantum group. It's okay, but for characteristic P, it's just not known at the moment really explicitly enough, even for SL3. Anyway, you can call this a sin, you can call this whatever. I mean, I want to describe the category anyway, so I shouldn't be too worried about the object. So let's ignore this for a second. Okay, otherwise I want to do the following trick. I tried really to compute in this category tilt using the definitions. I mean, this is hopeless. This is just impossible. Just try to find a category which I call VAP. I will click on the picture in a second, which is actually equivalent to the category of fundamental modules. So the category of generated by fundamental modules of your starting reductive group. In SL2, it's just generated by the vector representation by delta 1. It's a box down here. Okay, and this should work over the integers. Okay, so let's say you can find that, and then you would do some very general yoga. You would take some additive closures on both sides, and you would see that actually the additive closure of WEP would be equivalent to tilt. Not to rep, because I take an additive closure. It's not in the abelian category, but to tilt, to this additive category. Right, the analog of the projective models. So I would have, and that actually really works, and it works pretty fine in, let's say, types ABCD, and otherwise it's still pretty mysterious. Anyway, so let's ignore that. It certainly works pretty well for SL2, and you all know the answer for SL2. And I will click on the link in a second. But let's assume we know that. The next step I would do is I would have this explicit description of my category. And I would try to write down those idempotents in my category. I would try to find a basis in my category, which I call the standard basis. And this standard basis is just in characteristic P. It's just in characteristic 0. It's just a projection to the Weyl modules, right? This is an Artin-Wedderburn basis of my category. So projection to the Weyl modules, in particular, everything is super easy. It's an Artin-Wedderburn basis there. Orthogonal, complete idempotents, whatever you want to call And I would write down a basis with respect to my t bars. It splits of my t bars. And I would like to study the base change matrix between the two. Let me do this explicitly in a second, but yeah, let me just do it. Okay, so the idea is a little bit that, so there's a whole philosophy about this. It's called the light leaves philosophy. You can always write down, if you have some analog of Schur's lemma, you can always write down certain bases. For today, just take it as a black box. So you have 3 bases. One of them is defined integrally. It helps you to prove everything. It's my integral basis. One of them is this Artin-Wedderburn basis, which is defined generically, but all the idempotents are usually, or all the morphisms are usually not well defined in characteristic P. They have poles. And one of them is this tilting basis. And they do different things. The integral basis is just integral. It helps you to relate, as I said, categories for different characteristics. The standard basis is this Artin-Wedderburn basis. So the relations between the morphisms are trivial. And the tilting basis is the one you're interested in. And the tilting basis is the one you can specialize to characteristic P, because everything you write down will have no poles. You can write, so no poles, so the denominators will not be divisible by P. And with denominators, I mean, if you write down this basis in terms of the integral basis, right? That's why you have the integral basis. Write down this basis in terms of the integral basis, look at the denominators, none of them will be divisible by P, so you can specialize to your characteristic, and that's the basis you want. It splits off the tilting modules. And then you just need to study the base change matrix between the two. Why? Well, this has trivial relations. This is a relation, this has the relations you want to know. And well, just plot in the trivial relations, just use the trivial relations, use the base change matrix to get a list of relations on this side. Then you just need to simplify them, but you're basically done after you've calculated the base change matrix between the two. And what I claim is that this is just basically completely impossible, or almost impossible. You can write it down abstractly, but not explicitly, not that I know, for a tilt, but you can actually do it in this web category. In case of SL2, that's just a temporally leaf category, right? So it's very explicitly given by generators and relations, the monoidal category generated by the usual guys, like cups and caps, so evaluations and co-evaluations, and relations probably all of you have seen before, biojoint relation and whatsoever. Anyway, it's a very explicit category, and the philosophy is that this category web is equivalent to the integral version of my category tilt. So all I need to do is I need to write down idempotents, and I need to write down those bases here in this diagrammatic setup. Today, I'm not going to talk about diagrammatics. This is super explicit. Let me just mention that it's super explicit. You can do explicit calculations, and that kind of works for all. Let's say that works for A, B, C, D. I'm not saying we are able to do the calculations yet, but in principle, it works for types A, B, C, D. And the only reason why I don't mention the other types is because nobody ever cared about webs in type E6 or whatever. But in principle, it should work as well. So let me say it again. Try to find a combinatorial model of your category, which is diagrammatically given. In the diagrammatic setup, you always have these 3 types of bases. There is a general recipe to construct them. Okay? Write down these bases, write down the base change matrix between them, and you're done. You have described your category in terms of generators and relations. Why? Because in the middle, it's trivial. I mean, this is an Artin-Wedderburn decomposition, right? Where you get the quiver, which just has vertices and no edges. This is the one you want. You know the base change matrix. You know that you can specialize the right-hand side to characteristic P. This is exactly where I need my original sin. This is exactly where I need to know the tilting characters. And then you're done. You just do it. And the answer you get is actually pretty nice. So in the last 5 minutes, let me explain the answer. After, again, say it once more, the strategy is to use kind of a machinery in this diagrammatic part of representation theory, such that you can do calculations explicitly. Okay. and work over the integers as long as you can, then work over the rational numbers or the complex numbers in the middle. This is also defined over the complex numbers. Of course, everything is defined over the complex numbers. And make sure that the right-hand side has no poles, specialize it to characteristic P, and there you go. Okay, let me show you the answer for SL2. And you will see it's pretty nice. So before I zoom in here in my picture, this is my favorite rainbow. So this is the quiver for SL2. It looks pretty interesting. So how should you read it? So as I said, this should be the quiver. So this should be ZP in my equation upstairs. And I just wrote down the corresponding tilting module, T, that's here. I hope you can see it. Oops. I hope you can see it. And the corresponding highest weight up to whatever it is, 52. It's delta factors. You can see they grow. Well, here we have 8 delta factors, for example. Again, you could calculate this just using my negative digit trick, like inverting those digits along the p-adic expansion. And the quiver has arrows connecting the various parts. As you can see here, there's an arrow from 1 to 5, for instance, and there's an arrow from 5 to 17, and from 17 to 53, and so on. And if you zoom out, it looks exactly the same. So this quiver gets extremely fractal. So if I would have done it up to 150,000, it will still look the same, basically. Okay, and in order to tell you a little bit how the relations look like, let me do characteristics. Again, the same philosophy. Generation 0, characteristic 0. Generation 1, the quantum group. I show you generation 2, and then you might get a feeling how the relation look like in higher relations, in higher generations up to generation infinity. So this gets, as I said, infinitely complicated. It's a fractal. And yeah, just let me say it once. This graph is actually a fractal graph in the sense of graph theory. You can write down some nice fractal patterns. And you should expect that, right? Because you have this binomial, the binomials behave like Pascal's triangle characteristic P, which is kind of the blueprint, the prototypical example of a fractal. Okay, generation 0, okay. I have not 0 digits. I mean, in this case, the quiver has no edges. Okay, that's easy. Yeah, okay. There's not much more to say. Generation 1. So I just ignore, I take the quotient by ignoring all arrows. Let me go back here. So we have arrows of generation 1, which jump very, very short steps, like they're reflecting along certain hyperplanes. So this is just turning 1 digit around in my p-adic extension, right? So I told you, when I look at 26, I know what the Val factors are. So 25, 21, 30, 19. So I should have an arrow to 21. And this was a bad example. I sure have an arrow to 21. So that's how those arrow works, right? The arrows are connecting those successfully turning around the digits in the p-adic expansion. And when I say generation 1, I mean I turn the sign around in the zeros digit. Generation 2 is I turn the sign around in the first digit or in the zeros digit. Generation 3 would be, and so on, right? Okay, if I just ignore everything and just turn around signs in generation 1, then the quiver is just a line, and the relations are written down here, and the 0 just means I play a 0-digit game, right? The relations are what is called the zigzag algebra. So 2 steps to the right equals 2 steps to the left is 0, and each loop around each vertex, so up, down, down, up, is the same. It's kind of a zigzag algebra. And this is actually the underlying quiver for, if you continue this periodically, is the underlying quiver of the quantum groups generation 1. Okay, it's a line, and locally it looks like the zigzag algebra, like zigzag is the same, and going twice in one direction is 0, and going twice in the other direction is also 0. And you now wonder how it looks like in higher generations. It just gets, it just repeats itself. So in generation 2, meaning I have now 2 operators, 1, 0, 1, 1, turning around the digit in the zeros place, turning around the sign in the zeros place, turning around the sign in the first place, and they align themselves in a grid. And along each row, you again have a zigzag algebra. Along each column, you again have a zigzag algebra. And the relations basically say that squares commute. So zigzag algebra along rows, the same as here. Generation 1. You just stick generation 1 into the row, into the column, and the extra relation is that squares commute. And this goes on. This is just the general picture. Right? In general, so go to generation 501. Now you're not in dimension 1 anymore. Right? This is dimension 1 grid. You're not in the dimension 2 grid anymore, but you're in the dimension 500 and whatever grid. And in each row, you see generation 1. In each column, you see generation 1. In each higher column, row, whatever, you see generation 1. And you basically have some square commute relations. So it's kind of generation 1 glued to itself in a kind of infinite way, in a fractal way. So this is how you should read the square row. Along each generation, you have the quantum group, and the quantum group itself is kind of glued inside itself in a very funny way. Okay, and the point is, well, this is a very nice answer, and we basically know the answer for SL3. It's a bit harder to write down, but it looks like the same. Right? Now everything is supported on the positive dipole of SL3, and you have certain quantum algebra which is kind of glued into itself infinitely in an infinite complicated way. Okay, but I think I was only supposed to talk about 15 minutes, so I'm over time. So yeah, thank you very much for your attention.
Okay, thank you very much. Let's see, any questions?
Yeah.
So yeah, Dan has a question.
Yeah. So tilt is a symmetric monoidal tensor category.
Yeah, so he says tilt is a symmetric monoidal tensor category.
So does this equivalence do anything in terms of preserving tensor products?
So does this equivalence preserve tensor products?
Oh, that's a very good question. No, I was just asking, or we don't know how. I think yes, but currently we don't know. I was just asking the question to describe tilt as a category, not as a monoidal category. But I think that's also possible. What you need to do is you need to write down those idempotents and you need to decompose them again. The tensor product of those idempotents in the standard basis. And this, I think that's doable, but we haven't done it yet.
Oh, second question.
Yeah, second question. Wait.
So do you have any ideas what the tensor ideals would be inside of tilt?
Okay, so do you have any ideas what the tensor ideals would be inside of tilt?
Yes. So in this case, actually, so where's my cursor? Yes, my cursor. No, where? Oh, come on. Yes, my cursor. In this case, it's actually it's pretty surprising. So I say it again, we don't describe the monoidal category, but we can still describe the tensor ideals in this category. The tensor ideals in this category, you have infinitely many of them, and they are given by starting at the corresponding. So well, you have they're given by powers of p. So for each power of p, this is p equals 3. For each power of p, these are my red vertices. Here's another one. 9, 27 is the next one. For each power of p, you have a starting tensor ideal. And there's a nested sequence of getting tensor ideals that get smaller and smaller and smaller and smaller. So for each prime power, in particular, let's say if you would tensor T33 with any other module, you would never go down below 27. So that's how it works. So take some module in your tensor ideal, look what kind of highest weight it has. You will never go down to the next, below the next lowest prime power. And that's a complete description of all tensor ideals, like in one-to-one correspondence with prime powers.
So Ostrich actually does this for the quantum. So is there any sort of geometric interpretation here?
Okay, so Dan says Ostrich does this for the quantum group. So is there a geometric interpretation of this?
So the idea is the following. So what Ostrich does for the quantum group is, if I remember correctly, is basically saying that there's a one-to-one correspondence between cells in the affine Weyl group and tensor ideals in tilt. And the same should be true, but nobody ever proved it for P cells in the affine Weyl group and the corresponding ideals in tilt. And P cells have a geometric interpretation in terms of parity sheaves.
Okay, yeah, he's happy. Okay, any more questions? It doesn't seem to be the case here. What about the people at home? Any questions? Can you maybe go back to the slide about the home spaces, dimensions about the home spaces?
I can. This one?
Yeah, so for example, so I have a elementary question maybe. I don't know if there's an answer, but I don't know. Let's take, for example, so my question is there essentially a geometric interpretation of the dimension of these home spaces between the tilting modules? Because what I'm thinking is, so dimensions, so let's take category O, for example, parabolic category O. And I have dimension of home spaces between projectives. Then this is the dimension of some cohomology of intersections of irreducible components of Springer fibers, right?
Yes.
So is there some geometry here which also realizes these dimensions?
Yes, there is. I can't give you a precise answer. So all those ends of those tilting modules, they show up for the corresponding Zirkel bimodules, and Zirkel bimodules are equivalent to certain categories, parity sheaf categories. So yes, everything here is a geometric interpretation. And just to fill up your category O example, you could have said the same for tilting modules actually, because category O is what is called Ringel self-dual. So whatever you say about projectives will be true for tilting modules in category O as well, if you kind of multiply with the longest element.
Okay, I see.
So it's exactly the same story, it just gets more complicated.
I see. Mm-hmm.
Yes, I should have mentioned that. The category O is kind of the finite Weyl group case of tilt. Tilt is kind of the affine Weyl group case.
Okay. Yes. Thank you. Any more questions? Jack's question. Okay. So I don't think there are any more questions. So yeah, let's thank the speaker again.
Thank you, Daniel.
Thanks a lot. It's very interesting.
Thank you.
It was a pleasure.